A tennis ball with a mass of 50 grams is thrown vertically downwards. It accelerates at 9.6 meters per second squared downwards and strikes the ground after 4.07 seconds. At what height was the ball thrown? Height is just the displacement, and it starts its whole journey at 120 meters above the ground. Using the graph, determine the approximate velocity at 2 seconds. At 2 seconds is over here, and velocity is the gradient of a displacement time graph. So you're going to land up ruling a line that touches the graph at just that one point, and then determining the gradient of that line. So it lands up being, let's say, we go to 115, and that's at 1 second. So it's 115 and 1. And the next point we'll make is at 3 seconds, and that is true at 55. So then the gradient is equal to velocity at 2 seconds is equal to change in y over change in x, and that is equal to negative 30 meters per second, or approximately negative 30 meters per second. At which time interval does the ball experience free fall? Free fall is whenever it is only under gravity. So then you're going to land up with everything up until here, and then it's in there, so it turns out to be 0 to 4.07 seconds, and from 4.85 seconds to 6 seconds. Show that the ball was thrown at a velocity of 10 meters per second downward. So we're trying to find the initial velocity of this ball. Let's see what information we have got for that. So we can say S is equal to ut plus a half at squared. I know that at the top of its projectile it went 120 meters downwards, and I don't know the initial velocity, but I do know that it took 4.07 seconds to reach the ground, plus a half. We know that we were going downwards at 9.6, not 9.8. Notice that I have kept the displacement and the acceleration both at the same sign because they're both down, and then it's 4.07 squared. And the u turns out to be 9.9 meters per second, which is approximately equal to 10 meters per second. Then the next one, show that the velocity of the ball the moment just before it hits the ground is approximately and 49 meters per second, so that's a final velocity. So v is equal to u plus at. My initial velocity, they've told me, is 10 down now, plus 9.8 down, sorry, 9.6 down. And the time is 4.07, and that is equal to 49.04 meters per second, which is approximately 49 meters per second. The other thing is to note that in this story, the gravitational acceleration was 9.6 meters per second squared. That doesn't mean it's always 9.6. It just means in this one it is. Actually, in Joburg, it is around 9.6 rather than 9.8 because of our altitude. So this was just a slightly different question. If they don't give it to you, use 9.8. New method of delivering pizza to high-rise buildings is by drone carrier. The drone moves vertically upwards at a constant velocity. So I've got an initial velocity of 3 meters per second up. On a test run, the pizza is released 5 meters above the ground, so the displacement is obviously going to fall 5 meters down, and it's going to be under gravitational acceleration, which is going to be 9.8 meters per second squared down. If you're careful with signs, it all works out in the end. So calculate the speed that the box first hits the ground. V squared equals u squared plus 2as. It's a final velocity. So it's 3. I'm going to keep up as positive, and therefore down will be negative. So it's 3 squared plus 2 times negative 9.8 and negative 5. And I land up with an answer of 10.34 meters per second. And then the next one is calculate the time taken from the moment it is released until it hits the ground. So we're going to say V is equal to U plus AT. I could have used S is equal to UT plus half AT squared, but I'm going to get a quadratic, and I'd rather just potentially carry my own mistake. So this V over here was turned out to be downwards as well. It would have been a negative answer. And so I'm going to say this is down 10,34 is equal to 3 up plus negative 9,8 t, and my time will turn out to be 1,36 seconds. I'm then asked to sketch a displacement time graph for the released pizza box. Use the ground as your zero reference and include your key values. So it's displacement time. Initially, I'm 5 meters above the ground. The pizza box will go up at 3 to start, stop in mid-air, come back on itself, and then continue all the way down to the ground. And I know that this takes 1,36 seconds, and I haven't really got very much more information than that. The following graph, or the graph below, represents a ball that is released and allowed to bounce before being caught after 1,4 seconds. How many times does it bounce? So it's released, it speeds up, it hits the ground. Bounce 1. Then it comes back on itself, goes up into the air, stops in mid-air, lands up on the ground again, bounce 2, and does the same thing, but it doesn't bounce the third time. So it's 2 bounces, and if you like to say a land, but it's 2 bounces. Use the graph to calculate the height from which it was dropped. No equations may be used. So before it landed on the ground, this is a velocity time graph, and therefore height comes from the area under the graph. So I can actually just calculate that area over there, and I can say displacement is equal to area under curve, which is equal to a half of the base before it hit the ground, which is 0,04, times by the height, which is 4, and you land up with 0,8 meters. Why are all the solid lines parallel to each other? They are all the same acceleration, which is equal to gravitational acceleration. Why? Because they are in free fall. Students make a water bottle rocket as a project to investigate vertical projectile motion. They add water to the rocket, pressurize it, and launch it from the ground. On the way down, the rocket strikes the roof of one of the classrooms. They use video analysis to record the motion and plot the velocity time graph, which is shown below. Here's free fall. Here's free fall. This is the part where it's getting propelled upwards, so it has increasing velocity in the air. It's an acceleration, and it's due to the rocket. Here is the part where suddenly I am slowing down because of the roof. So, which law can be used to explain why the bottle rocket moves upward when the water is being expelled downwards? That is Newton's third law, and it says that for every action there is an equal but opposite reaction force. Define displacement. It is a body's change in position in space. At which points does the rocket first undergo free fall? It's from this point over here, so it's at point A. And when does it reach its maximum height? When it stops in mid-air, which is 0 velocity, and that is at point B. Calculate the height of the classroom roof above C, and again we are above the ground at point C, so that's over there. What has happened is this rocket has gone up into the air, stopped, and then come back on itself. So the height of the roof will be the first triangle minus the second triangle. So we're going to say Displacement is equal to area under curve. Which is equal to a half of the base. 0 to b is 2,45 times the height up to a, which is 22,5. It's the y of a, minus a half of the base up until point C. So between B and C is 350 minus 2,45, which is 1,05. And the height of C is 10,36. You've already got the minus in over here, so you can't put it in again. And you land up getting 22,12 meters. Calculate the velocity of the bottle rocket the moment just before it hits the ground, in other words, at point F. So we're trying to find that velocity over there. We do know what happened at E. It was going at 0 velocity. And we do know a time between E and F, and we know that it was in free fall between E and F. So we've got a fair amount of information, and we can say V is equal to plus AT, and that is equal to, my initial velocity is 0. My acceleration is 9,8. My time is 2,05 seconds. And then I land up with a velocity of 20,09 meters per second. It's positive, and I chose down as positive because the acceleration was downwards, and so that is down. And then finally it says sketch an acceleration time graph to represent the motion of the bottle rocket from the moment it was launched to the moment just before it hits the ground. It's not necessary to show any numerical values, so what are we going to do? We're going to say, excuse me, I definitely know that initially I had a positive acceleration. That's a very positive gradient, high positive acceleration. And then we had a negative acceleration at -10 for quite some time. Then we landed up at point C, hitting the roof, and we have a positive acceleration again. It's not nearly as steep as the first one, so we'll put it in like that. And then again we carried on at 9,8 acceleration time. And so the two green lines are there. Let's just do that. That's that line over there and that line over there. So those are represented on the acceleration time graph like that.